All right, so for number 46, what we need to do is we need to get it the molarity. And so we need to determine the molarity here and the molarity here. And so the first part of this is kind of a solutions dimensional analysis problem. So we have two percentages here. So it's 0.057% of 75% H3PO4. What does this mean by mass? And so what this means is this. I have 0.057 grams of 75% H3PO4 solution for every 100 grams of cola. So what I'm going to do is I'm just going to use some dimensional analysis to figure this out. And so the 75% H3PO4 means that I have 75 grams of pure H3PO4 per 100 grams of 75% H3PO4 solution. And so if I had 100 grams of this 75% solution, 75 grams of it would be pure H3PO4. And this tells us how many grams of pure H3PO4 we have. And then I need the molar mass for H3PO4, which I'll just look up because I don't want to calculate it right now. So if I go to Wikipedia, I can get the molar mass. 97.99. Usually I just go 2 decimal places. Oops, and this is upside down. So what do I have so far? The grams of 75% solution cancels. That leaves us with grams of phosphoric acid. The grams of phosphoric acid cancel. That leaves us with moles of phosphoric acid. Now I just need how many liters of cola solution I have. And so do they give us the density of the cola solution? They don't give us the density of the cola solution. So if they don't give us the density of the cola, what should we assume? We're just going to assume that it's close to pure water. If they gave us the density, then I'd put the density in here. But we don't have it. And so I'm going to assume that it's the same as water. And that is, if I have 100 grams of solution, that would be 100 milliliters of solution. So 1 gram, or actually, let's go with, I'm going to go with maybe 2 sig figs here. 1.0 grams of cola solution per 1 milliliter of cola solution. And so we're assuming the density of the cola solution is about equal to the density of the water liquid. Okay, so that gets rid of the grams of cola solution and leaves us with milliliters. And then I'm going to convert milliliters into liters. And so the milliliters cancel. That leaves me with moles per liter, which is the molarity. And so I'll calculate the molarity here. It should be 0.057 divided by 100 times 75 divided by 100 divided by 97.99 times 1,000. I'm allowed 2 sig figs. I'll carry 1 or 2 more. So at the lower limit, this would be the pH here. We would get the pH by going to Ka next. So if we want the pH, then we'll go H3PO4 plus water. This is going to give us hydronium plus dihydrogen phosphate. Ka1. Take a look what the Ka for phosphoric acid is. They give us the pKa here. It's 2.14 in Wikipedia. So I'm going to convert that into Ka. .24. Actually, we're allowed 2 sig figs here, so this will be 2 sig figs here. 7.2, and then I could store 4 times 10 to the minus 3. So I just set up the ice table here. And I'd solve for x. X is the hydronium, and therefore the pH is equal to the negative log of x. If I skip step 2, if it's not negligible, then I have to do step 2. How do I know if it's negligible or not negligible? I'll take a look at Ka2. Since Wikipedia only gives me the pKa values, I need to convert it. The pKa2 is 7.20. So the Ka is 10 to the minus pKa. And so I'm going to plug in 7.2 negative 10. 6.3 times 10 to the minus 3, 6, 7, 8. 6.30 times 10 minus 8. Yeah, you expect this to be negligible. And so step 1 is enough to determine the pH. If step 2 were significant, then maybe I'd do step 2. Okay, once you find the pH, this is one limit. The other limit is you repeat the calculation, but this time you use the higher concentration of phosphoric acid. Plug it in here, and then solve for your pH, and that would be the pH range. Does that answer the question? Okay. All right. On the practice test, and I'll talk about it now. There's a lot of different Chem 1A instructors here. And in Chem 1A, you're supposed to cover structure and pH. But a lot of people, they didn't cover this in Chem 1A. So you might not have had this as well. So if you haven't had that, you're gonna because I skipped it during the lecture, and so let me give you just the brief rundown on how to do 7, 8, 7 and 8. 9 is similar, but let's look at 7. Which acid is strongest? And so there are different ways we can answer this. One, we could just look it up. If we have the acid chart, we could just look it up. Which one's the strongest acid? But the problem is only one of these is on the acid chart, A, acetic acid. The other 3 aren't on the acid chart. And so how do we figure out which one of these is strongest? Well, what we do is we do it like a structural analysis. There are 3 things that we look at when we try to determine acid strength. At least 3 things. So what are those 3 things we look at? The first one we look at is the polarity. The polarity, what I mean by polarity is the polarity of the bond to the hydrogen. That is, the more positively charged that hydrogen is, the more acidic. And so we want a bigger delta plus. The more positive, the stronger the acid. The second factor we look at is the stability, the conjugate base. The stability of the conjugate base, the more stable it is, the increasing stability, the stronger the acid. The most important thing, though, which I say for last, but sometimes it doesn't matter because they're all the same, is the bond strength or the bond energy. The weaker the bond, the stronger the acid. So the most important one of these is the bond strength. And the bond strength typically will dominate over the other two. So let's take a look at the choices we have here. So what we do is we look at these. What I'm going to do is I'm just going to look at the two extremes here. I'm going to compare A, which is acetic acid, to D, which is trichloroacetic acid. And so if I look at A, let's go ahead and draw the Lewis structure. And compare that to D. What I see are both of these are carboxylic acids, because carboxylic acids are defined as having this functional group, the carboxyl group here. The only difference is this R group. The R group, this is the rest of the molecule here, the R group. And so if we have the carboxyl group here, which is an acid, attached to two different things, over here we call this a substituent. And so over here we have what we call the methyl substituent. And over here this is the trichloro substituent, trichloromethyl substituent. And so here the R is equal to methyl. Over here the R is equal to trichloromethyl. To understand what these two substituents do to the acid, the carboxylic acid, we have to take a look at analyzing this in more detail. So for example, acetic acid has 4 hydrogens. Since acetic acid has 4 hydrogens, would you call it a tetraprotic acid? Is acetic acid tetraprotic? Is it triprotic? Diprotic? Monoprotic? Monoprotic, Tristan? Why is it just monoprotic? It has 4 hydrogens. Only one hydrogen is acidic. These 3 hydrogens here are not acidic. This hydrogen is acidic. What makes this hydrogen acidic and these non-acidic?
Is it the willingness for that singular hydrogen to break off?
Well, the willingness to break off, if we look at the bond energies, hydrogen-carbon bond is a little bit weaker than an oxygen-hydrogen bond. It turns out the oxygen-hydrogen bond is a little stronger. And so if you're just going to argue about the willingness to break off, this should break off easier because it's got a little weaker bond. You know, not a huge amount, but it's weaker. And so this one should go in terms of bond strength. But it isn't just bond strength. If it were bond strength alone, and we're done. It would be, you know, triprotic, probably. Yeah, it has to do with polarity. Because what's breaking these hydrogens off? What's breaking these hydrogens off is a base, and the base has to be able to latch on to the hydrogen. And the base is like hydroxide. You know, hydroxide's negative. Negative's looking for positive. And so if we look at these hydrogens, the electronegativity difference between hydrogen and carbon is very small. It's about 0.4. Hydrogen's at 2.1, carbon's at 2.5, so they're very similar in terms of electronegativity. And so this one, you know, if a hydroxide comes, it's not even going to notice this that much because it has so little positive charge. Hydroxide is like one of those things. It's just looking for positive charge, and so it'll just pass by, you know, you know, I guess. Whatever, like, you know, mosquitoes or zombies or whatever. You know, they're looking for something, and this is it. And so it's got that positive charge. It can latch onto this, and then tries to pull it off. So it gets in a tug of war here and tries to pull it off. So that's what we're looking for. And so in terms of polarity, this would be the most polar. And what was the other thing to look for? Stability of the conjugate base, but we'll have to look at that later. So we're primarily looking at just this hydrogen here, just this hydrogen here. And what makes this positively charged? So there are different ways we count the electrons. And so let's take a look at the ways we count electrons now. One way we count the electrons is via the octet. And so if I look at this carbon has an octet of electrons. So that's good. This carbon has an octet. This oxygen has an octet. This oxygen has an octet. So pretty much everybody has an octet. And the hydrogens have a duet, but that's okay. And then over here, this carbon has an octet. And it's the same. All of these have an octet. So that's one way. The octet rule's been satisfied. The octet helps us determine if it's a reasonable structure or not. And so that's one way of counting electrons. The other way of counting electrons is formal charge. Formal charge is also very useful in determining Lewis structures. So for formal charge, what we do is we make an assumption. What do we assume with formal charge? We assume that we have 100% covalent bonds. A 100% covalent bonds means we split the bonds evenly. That is a 50-50 split of the bonding electrons. And so what that means is that in this bond here we have two electrons. One electron goes to hydrogen, the other goes with carbon. And then we total up all the electrons. So hydrogen ends up with one electron. How many valence electrons does hydrogen normally have? It normally has one valence electron. So its formal charge is 0. In fact, all these hydrogens are the same. And so all these hydrogens here will have a 0 formal charge. And then this carbon ends up with 4 electrons. That's going to give it a 0 formal charge. And we do the same thing over here. This carbon ends up with 4 electrons. That gets a 0 formal charge. This oxygen ends up with 2, 4, 6 electrons. It normally has 6 valence electrons. It's 0. This is 0. This is 0. So formal charges we normally circle like this. So all the formal charges are 0. How about over here? So we divide it 50-50. %, covalent means 50-50 sharing of all the bonding electrons. What are the formal charges here? Well, chlorine has 1, 2, 3, 4, 5, 6, 7. How many valence electrons does chlorine normally have? It normally has 7, so the formal charge here is going to be 0. So all the chlorines have 0 formal charge. In fact, all formal charges are 0. We normally don't show 0 formal charges. We typically just show the non-zero formal charges, but in this case I just want to emphasize it. So when we assume 100%, we split the bonding electrons. It's going to be a 50-50 split of bonding electrons. Lone pair electrons aren't split, just the bonding electrons. So these chlorines retain all the lone pair electrons there, 2, 4, 6, and then the bonding 7. All right, that's formal charge. The other way of counting electrons is via oxidation state. For oxidation state, what do we assume? Well, we assume the opposite of what we did for formal charge. We're going to assume 100%. What's the opposite of covalent? Ionic. 100% ionic bonds. This means winner take all. The winner is going to be the more electronegative species. Winner takes all. Unless it's a tie. If the electronegativities are the same, then it's going to be a tie. So we divide up the electrons differently here. So hydrogen versus carbon, who wins? Well, carbon's electronegative is 2.5, hydrogen's 2.1. Carbon wins. Carbon versus carbon, they're both 2.5, so this is going to be a tie. We can't have winner take all here, because there's no winner. And so that leaves with carbon with 2, 4, 6, 7 electrons. Carbon's supposed to have 4 electrons. And so what ends up happening is we end up with a -3 oxidation state. It has 3 extra electrons. Hydrogen ends up with no electrons, so that's going to come out to 0. Oxidation states I put parentheses around. Formal charges I circle. Okay, carbon versus oxygen. Oxygen's going to take all. So carbon only ends up with 1. Or actually, yeah, 1 electron, because we're going to have a tie here. And so this carbon here is going to be +3. This carbon here is -3. Okay, and then this oxygen here takes all the electrons. It ends up with 2, 4, 6, 8. It's supposed to have 6, so it has 2 extra electrons, -2. This one takes all the electrons here, 2, 4, 6, 8, and we end up with -2. This hydrogen is going to be a +1. Here. Okay. Let's take a look. Can you do the oxidation states here? Try it and see. So the formal charge is 0 for this chlorine. What is the oxidation state on that chlorine? -1? Yeah, that's right. So all these are the same at -1. What's the oxidation state on carbon? This carbon here. +3 is correct. Here it's going to be a tie. You know, there's no winner. So it ends up with 1 electron. It's supposed to have 4 electrons, so that's +3. How about this carbon here? It's also +3. All the other atoms are the same. You know, it's going to be +3. The last way we count electrons is this. Let's focus in on the carbon here, on the substituent. This carbon, the oxidation state is -3. The formal charge is 0. So with formal charge, we're assuming a 100% covalent bond. With oxidation state, we're assuming a 100% ionic bond. But the true state of bonding is somewhere in between. And so if this carbon is here, between 0 and -3, we don't know what that number is. We need some quantum mechanics to actually calculate it. And so what we say about this carbon is it's somewhere in between there. We don't know the exact number, so we'll just call it delta minus. Delta is the partial charge, delta. However, when we look at this carbon is somewhere between 0 and +3. And so this carbon is a delta plus carbon here. It's like the hydrogen. If we look at this hydrogen, the acidic hydrogen here, it's somewhere between 0 and 1. And so we call it delta plus. And so we could do this with all the atoms here to figure it out. And so probably the easiest way to see the difference between these, since I have too much writing there, when I look at this substituent here, the oxidation state is -3, versus when I look at this substituent here, the oxidation state on this one is +3. So what we do is we consider this an electron-rich substituent, whereas over here this is electron-poor substituent. How's that going to impact the acidic hydrogen? The way it impacts is due to the inductive effect. The inductive effect is this electron withdrawing. So this oxygen's pulling electron density here, which in turn is going to pull electron density away in this manner here. And we end up with a delta plus on the hydrogen. This carbon over here is quite rich, but when I look over here at the inductive effect, I have this oxygen pulling electron density away, but also this carbon is going to pull electron density away, which will result in this bond becoming even more polar. In fact, this becomes so polar, you know, the bond strength is about the same. This becomes so polar that this is no longer a weak acid. This trichloroacetic acid is a strong acid. It's not one of the ones you have to memorize, but it's a strong acid. Whereas acetic acid over here is a weak acid. We didn't look at the stability of the conjugate base. But based on the polarity, trichloroacetic acid should be stronger. It turns out that based on the stability of the conjugate base, it also predicts that trichloroacetic acid is stronger. And so let's take a look at the conjugate bases here. And we're going to look at bases in general. All right, for acids we want positive charge. The more positive charge, the better. That gives the base something to grip onto. For bases, we want the opposite. We want more negative charge. And so acids, positive charge, bases, negative charge. But when we look at negative charge, we have to look at localization. Localization is just concentrating that negative charge in a small volume of space. Versus delocalization. Delocalization is spreading out that negative charge over a larger volume of space. And so concentrating versus diluting the negative charge or spreading it out. The more we can distribute the negative charge over a larger volume, the less basic it is, the weaker it is. So strong bases are unstable, reactive. Weak bases are stable, less reactive. And so in terms of stability, we want to form a weak base. So let's compare the two conjugate bases. The conjugate bases are going to form after the acetic acid loses a proton. If acetic acid loses the acidic proton, it forms acetate. We'll take a quick look at acetate here. And the thing about acetate is there is resonance delocalization of the charge here. Because the charge is not localized on this oxygen, it can be delocalized onto the other oxygen here. It turns out that neither of these structures is correct. Do you know what the best structure for this is? This is what they say is one of the failings of valence bond theory. Can you tell me what valence bond theory states? How does valence bond theory describe a bond? Valence bond theory versus, do you know what the other theory that we use to describe bonds, molecules? What it's called? Molecular orbital. So what's the difference between molecular orbital theory and valence bond theory? Which one is more powerful? Are they equal, or is one more powerful in the sense that it can predict a lot more stuff than the other? I got a comment that the students going on to organic chemistry are very weak in valence bond theory. They don't know what valence bond theory is, and so it's a problem because they should learn it in Chem 1A, what valence bond theory it is, but maybe by the time they get to organic they've forgotten it. But you need it, you know, to analyze structures in organic chemistry. So if you're continuing on in organic chemistry, you need to know this stuff in detail. But in valence bond theory, we treat the bond as being overlap of atomic orbitals. In a molecular orbital theory, what we do is we combine the atomic orbitals to make new orbitals called molecular orbitals. We do a linear combination which results in a bonding and an anti-bonding. And we describe bonds as being a net bonding. That is, the electron densities mostly in bonding orbitals, which is favorable because it puts the negative charge in between the two nuclei, versus antibonding, which puts the negative charge density outside of the internuclear region, which causes the nuclei to repel. But basically, MO theory is a bit tough, because MO theory, if we look at quantum mechanics, you know, the theory of molecular structure, the theory of bonding is quantum mechanics. And in quantum mechanics, we do, when we treat it to bonds, we use molecular orbital theory. And so molecular orbital theory is the full quantum mechanical treatment of the molecule. But the problem is we don't have the computer to do this. I had a lab set up. Where we would do a full quantum mechanical treatment. And what we do is we look at different factors for this. Probably the easiest thing to do quantum mechanically is something like this. So I forgot to resume the recording. So basically we're looking at this, the hybrid structure here. In trichloroacetate, we also have resonance delocalization. And so both of these have resonance delocalization, and the negative charge is delocalized over two oxygens. So are they the same in terms of base strength? No, because there's something called inductive delocalization as well. And so let's compare the oxidation states, because the formal charges are the same, octets are the same, the only difference is the oxidation state. So let's look at the oxidation state of the substituent here, or the inductive effect. If you recall, the oxidation state on this carbon is 2, 4, 6, 7, minus 3. However, the oxidation state on this carbon is plus 3. So if you have this, methyl groups are thought of as electron rich and electron pushers. So we have a lot of electron density here. This is electron rich. If methyl is electron rich, it's going to make it more basic, because it's going to push negative charge out to the oxygens. Over here, this is electron poor. And electron poor is going to make it less basic because of the inductive effect. So here we're going to have an inductive. This is plus 3 because of all these chlorines here withdrawing electron density, which in turn is going to withdraw electron density here. Versus this is kind of pushing, you know, electron density towards that.
Could you explain why electron richness or poorness affects the acidity or basicness of solution?
How it affects the acidity or basicity? The electron, which one?
Yes.
Okay, this one is less basic, because what we're looking at is the negative charge on the oxygens. Due to resonance delocalization, we determine the negative charge is minus 1/2 on each. But what happens is this carbon is electron hungry. This carbon being electron hungry is trying to suck the electron cloud away from this carbon, even though, you know, officially they're supposed to be tied, but no, they aren't tied, because this one is, and in effect, even if they were tied, actually they are, this one's plus 3 as well. it's putting up more of a fight versus this one. This one's so rich, it can push electron density towards that carbon over here. And so this one has an electron withdrawing effect here, which is going to withdraw the negative charge density here. And so it's being pulled towards the structure. Whereas over here, this is -3, and so it's going to push this, and that's going to make these more negative. Does that make sense? And so, in other words, based on the substituent, this is an electron-rich substituent, this is an electron-poor substituent. If we want to make it more basic, we put the electron-rich. And so this is a stronger base here. If we want to make it less basic, we put on electron-poor substituent, and this will be a weaker base. The base strength is going to depend on how much negative charge you have on those oxygens. The more negative charge you have on the oxygens, the more basic. And so the stronger base, because greater negative charge on the oxygens. And you go, well, the negative charge is -1/2. Well, yeah, but it's going to be impacted. That -1/2 will be impacted depending on what substituent you have here. And so we have a methyl substituent, which is quite electron rich. It's -3. It's pushing. Versus a trichloromethyl substituent here, which is electron poor. It's pulling. So we have pushing versus pulling electron cloud density away. And so this is going to result in decreased negative charge on oxygen, on O. Yeah. Does that answer the question, or were you asking something different?
No, pretty much.
Okay.
As far as explanation and verification.
So we look at two things. This is called inductive. So we had resonance delocalization and inductive delocalization. And so for delocalization, we look at both. The most important delocalization is resonance. And the other type of delocalization is inductive. It's good if we have both of them present. And so let's go back to the thing we were looking at earlier. See how much time. Look at number 8. Which base is strongest? So we just did acetate. Let's compare acetate to B here. B is a benzene ring attached to this oxygen here with a negative charge. This is called phenoxide. And benzene ring as a substituent is C6H5. This is called the phenyl group, the phenyl substituent. And we have phenoxide here. And we can compare that to phenol. Phenol is an unusually acidic alcohol. It's like acetic acid, but it's an alcohol. Alcohols aren't usually considered very acidic. So let's take a look at an alcohol like methanol. So these are both alcohols, and therefore they're both going to have about the same polarity here. And then they're attached to these carbons. Like this carbon here is -3, the oxidation state. This carbon here is 1, 2, 3, +1. So that's an electron withdrawer, but these carbons over here could be negative as well. We look at additional carbons, so we start labeling the carbons. Here's our initial carbon, then we could have other carbons on there. So for example, here, if we had more carbons on here, a longer chain, that changes the electronic environment. Here, so let's say we had a carbon here. It depends on what this carbon's bonded to, but the more carbons we have in this chain, the more electron rich it is. So let's just do this. And we'll put hydrogens here. This carbon's going to be the oxidation 2, 4, 6, 7. This carbon's going to be a -3. This carbon is going to be 1, 2, 4, 5. This carbon's going to be a -1. So even though we only have a -1 carbon here versus a -3 carbon here, we got another carbon over here that's -3, whereas these are just hydrogens at +1. Now the closer we are to the alcohol, the more impact it's going to have, but this will have an impact here as well. All these are electron-rich groups here, so we start looking further. But what we can say is that compared to a normal alcohol, this is a 6-membered ring. And so if we take phenol versus cyclohexanol, this is a weak acid. Cyclohexanol which has no double bonds here, has a Ka that's so low it's not even considered an acid. So this is a very, very weak acid. Essentially we could consider it non-acidic. The only time it will act as an acid is if you have an exceptionally powerful base. And what's the difference? The difference is in localization versus delocalization. And so if we look at phenoxide versus, let's look at methoxide. So I'll try to keep it short here. If we look at phenoxide, this is one resonance form for phenoxide, but anyway, what can happen here is we can delocalize the electrons. So we have an sp3 oxygen here. This lone pair on the sp3 oxygen can go into the bond, so this is going to form a double bond here. But now this carbon is going to have too many electrons, so we're going to have to kick out these double bonding electrons and then place them on that carbon. So the structure is going to look like this. So what we've done is we've moved the negative formal charge from this oxygen here to this carbon here. Now we have the negative formal charge there. These are non-equivalent resonance forms. The energies are going to be a little different because over here we have the negative formal charge on this oxygen on top, and down here we have it down on this. We've also changed the hybridization. This went from sp3 hybridized to sp2. The carbon went from sp2 to sp3. Okay, we can continue this. That is, these lone pairs can come down into the bond, and then it kicks these ones out here. Okay, and then we end up with the negative formal charge here. And then we can move these ones down here and then kick these ones out here. And we come up with another resonance structure. In which the negative formal charge is now on this carbon here. And so we have resonance delocalization. We could also have inductive delocalization too, in addition to resonance. And it depends on what we put on these carbons here. So for example, we give names to these carbons because we look at the structures beyond the main atom here. And that is these two carbons that are adjacent to this substituted carbon are called ortho. These ones here are beta, and this one on the opposite end is para. So for example, if we put a substituent on the ortho position, that could change the basicity. Actually, let me go back to the original. So let's say I remove the hydrogen and then put something else here. Let's say I put an R group here. And the two R groups I have are methyl. If I put a methyl group here, will it make it more basic or less basic? So if there's a methyl group here and I have a negative formal charge here, is that leading to more stability or less stability? Now is a methyl group electron rich or electron poor? Electron rich. And so if you have an electron rich methyl group next to an electron rich carbon, is that favorable? Negative likes negative. Favorable? No. Versus what if I put a trichloromethyl group here as a substituent? If I put a trichloromethyl group on the ortho position here, that's electron poor. And so if I had a trichloro group, instead of this hydrogen, it's going to suck electron density. If it sucks electron density here, it's going to stabilize the negative charge here, making it more stable. Correct? And so that's favorable. And what that means is this. Methyl substituted here is going to be more basic, whereas trichloro is going to be less basic. And that has to do with the inductive delocalization in addition. And so here we could put a methyl or a trichloro. And it's going to result in a difference because one, methyl is going to be a -3, trichloro is going to be a +3 oxidation state. So this is going to be quite a big difference, electronic. We can also think of this in terms of inductive effect. If we put the trichloro there, then the inductive effect is going to be pulling the electron density away from this oxygen. So net effect is like this. That's with this one. However, if we have this one, then it's kind of pushing electron density out. And so we have this pulling effect and the pushing effect. The pushing effect is going to make it more basic, is going to concentrate the negative charge. Whereas the pulling effect is going to make it less basic, delocalizing the negative charge. So going back to this list here, we take a look. Both of these will be weak. Which one's weaker? Well, in organic chemistry, they give you a simple rule. The simple rule is the more resonance forms you can draw, the weaker it is, the more stable it is. And since we could draw more resonance forms for B than A, then we might suspect B is more stable. But there are other factors in there too. That's often what's done. Whereas if we look at methoxide, there's nothing. There's no delocalization. In fact, it's worse because you don't have any electron withdrawing. This carbon is, what is it, 2, 4, 6. This carbon is -2. So that's still electron rich. And so it's pushing. And so we expect this to be a strong base. And in fact, it is a strong base. This is one of the strong bases I don't think you have to memorize. And if we compare this to hydroxide, what do you think should be a stronger base? Methoxide versus hydroxide. Which one do you think is stronger? Methoxide. I would think methoxide is stronger because you have electron-rich group versus a hydrogen. Here. This hydrogen, the oxidation state's +1. So I would predict this would be stronger, but there are other effects too, like the bulk. You know, this is a lot bulkier group than a hydrogen. So the bulkiness might slow down its reactivity, you know, versus this, which would be more nimble in terms of reactivity, like a sumo wrestler versus a regular wrestler, let's say. All right, so let's continue on with this. Ammonia. Ammonia is not a full charge, it's a partial charge. And it's localized. There's no delocalization, whereas methoxide is a full negative charge. Ammonia has a partial. So we'd say this so far. And then we have trifluoromethoxide. Trifluoromethoxide versus methoxide. Both of these have a negative charge on the oxygen, so are they equal in strength? No. This one is very weak. Why? Yeah. This is an electron withdrawing group. And carbon's electron poor. If we look at its oxidation state, it is +4. This really maxed out. So this is quite poor. So very weak. And that has to do with the inductive effect. And so the same thing here. Normally when we do the inductive effect, we just look at the fluorines pulling electron density away from the carbon, making the carbon more positive, which in turn pulls electron density away from the oxygen, making this oxygen less negative. Whereas over here, it's working in the reverse direction. This is electron pusher versus puller. Alright, so when it comes back down to this, it's going to be C. This is resonance delocalization, less negative, inductive delocalization. Okay. All right, let's take a break, and then we'll talk about the lab, and we're just going to start the lab today. And we're going to continue this lab for 4 periods. The goal is to determine the presence of species. So we're just going to try to detect if any of these species are present. And so if we get a positive test, then that species is present. If we get a negative test, then that species is not detected. It's not detected, but it could still be present. That is, it could be that you have such a low concentration, it's below the detection limit. But anyway, we test a lot of these individually. So we have individual tests for these. And then we have an individual test for this and an individual test. So these are going to be individual tests. So we'll take a sample and then test it directly for the presence of sodium, ammonium, sulfate, nitrate, etc. However, for these, we have a problem with interfering reactions. What we do is we take advantage of the chemical properties of these in order to detect their presence. And when we do the chemical reactions, there's a potential for interfering reactions. To prevent interfering reactions, we have a qualitative analysis scheme, which I'll just call qual scheme. And so a lot of these will behave similarly. And so what we need to do is we need to separate them out one at a time or more. And so here we're going to be looking at these ones here. For ammonium and sodium, we do it in part 1 here. So in part 1, we do the ammonium test, which we take a sample and then do a couple of chemical reactions to see if ammonium's present. For sodium, we do a flame test. The flame test for sodium, we use a platinum wire. Well, the problem is sodium is a very intense signal. In fact, the signal is so intense, we have the opposite problem. So the opposite problem is it's always detected. And if it's always detected, that means we get a false positive. And so the problem with sodium is a false positive. That is, it's not present, but you still got a positive test. How is that possible? It's possible because of contamination. Everything you touch, you leave sodium ions on. And sodium is so sensitive that it doesn't take much to get a positive test. So this is a false positive. And so that means what we have to do is we have to clean our platinum wire very thoroughly. But it's really hard to clean these platinum wires. It takes anywhere from 30 minutes to 1 hour to clean the wire. And if we're going to invest that much time cleaning the wire, then what we're going to do is we're going to combine the flame test here, because we're also going to test calcium as well. Calcium gives a red flame, sodium gives a yellow flame. Now, the problem with sodium is it's too intense. The problem with calcium is it's very weak. And so if you have both sodium and calcium present, the sodium will completely drown out the calcium. You wouldn't be able to see the red flame. You'd need a spectrometer to see it. So to prevent having to clean this multiple times, what we're going to do is we're going to do the flame test together. So once you hit this part of the flow chart, we're going to first test calcium, and then we're going to take a fresh sample of our unknown, this is called the unknown solution, and test for sodium. That way, calcium burns off in seconds. So you'll see the red flame, and then anywhere less than a minute later, it's gone. Anywhere from 10 seconds to a minute. Whereas sodium just persists and persists for an hour. And so we'll just clean it once here. So we're not going to do the flame test today. In fact, let's not even do the ammonium. Instead, what we're going to do is we're going to do the start of the flow chart. So 1 is not part of the flow chart. 1 is totally separate. 2 is the first step of the flow chart. So we're going to go to 2. And so what we're going to do is we're going to test this solution here, which should contain these species. Now the first step in this test is to remove silver. The way we remove silver is this. We can take a look at the procedure. Let me look at the procedure. So number 1, we're going to skip that for right now and go to the first step of the flow chart. Now the flow chart is a qualitative analysis scheme, and the way it's been developed is to minimize interfering reactions. And so we have to do this in order. So once we start number 2, we got to follow this in this order. We won't always have each step to do, but we're going to go in the sequence. So the first step is we're going to take 10 drops of the original solution to be analyzed in a small test tube, add 5 drops of distilled water, 2 drops of 6 molar HCl, stir well, centrifuge, reserve the decantate for procedure 3. Wash the precipitate with 10 drops of distilled water, centrifuge, and add the washings to the decantate. Dissolve the precipitate in 4 drops of 6 molar ammonia, and then add 6 molar HNO3 to the ammoniacal solution until it is acidic to litmus. Caution, nitric acid can cause severe burns. Avoid contact with it. If you come in contact with it, immediately wash the area with copious amounts of water. A Curdy white precipitate of silver chloride confirms the presence of silver ions. So I don't like the procedure like this. What I like to do is I like to, in my lab notebook, what I do is I just photocopy this flow chart and just tape it into my lab notebook or staple it into the lab notebook. And then I'd have the procedure here. And so the thing I need to know is how much, I don't even need to know how much. I just need to know it's 6 molar HCl that I'm adding. The reason I don't need to know how much, well, I need to know how much unknown. I need to start off with 10 drops of this solution here. And then it tells me to add water. I'm not going to add any water. Because if I add water here, it says distilled. We don't have distilled, we have deionized. But if I add the deionized water, what I'm going to do is I'm going to dilute it. Is it easier to detect dilute or is it easier to detect concentrated? Unknown. It's easier to detect concentrated, so whenever it says dilute, I skip it. I don't bother diluting it. It just seems like a waste. So I'm going to just take my 10 drops straight and then add my 6 molar. Now, how much 6 molar? It says to add XX drops of 6 molar. I'm not going to bother with that. I need to do one thing in this step. What do I need to do? I need to make sure I precipitate out all my silver. I need to precipitate out all my silver by adding chloride to this to form silver chloride. Now, how much HCl do I need to add? I need to add HCl until it stops precipitating. When it stops precipitating, then stop adding the HCl. But the problem is, it's hard to tell when it stops precipitating, because when you add the HCl to this, what you're going to get is you're going to get a cloudy white suspension. And so as you add more HCl, you can't see, am I getting additional cloudiness or not? Since it's so difficult to see, what we do is we centrifuge this down. And when we centrifuge this down, it's going to compact the precipitate to the bottom, and then we should have a clear layer on top. To the clear layer on top, we add another drop of HCl. If we add another drop of HCl and it turns cloudy, then keep adding. And so we got to repeat this over and over until it's completely precipitated. It doesn't take much, though, fortunately. But we need complete precipitation. So how much HCl? You add enough for complete precipitation. That's how much you add. The problem is they tell you how much to add. Sometimes that's enough, sometimes it's not enough. If it's not enough, what happens is the silver creeps into this other branch of the flow chart. If silver creeps into the other branch, it screws up these reactions here by causing interfering reactions, and you get weird results that you don't know what's going on. All the colors are messed up and everything else. So what we need to do is we need to have a clean, complete separation. And so we're separating out the silver as white silver chloride solid. And then we're saving the solution. So on the bottom here we have what's called the precipitate. On the top here we have the decantate, or the supernatant. The decantate we have to save. We can't throw it away because the decantate contains the remaining cations. And we're going to analyze that for those remaining cations. The problem is the precipitate is, how do you separate the decantate from the precipitate? Normally the way we do that is by filtration, but filtration is too time consuming. So the way we're going to separate it is by decanting. That's why they call it decantate rather than a filtrate. You know what decanting is? Decanting is you either get a pipette and suck it off the top, or you just pour it out. Most people just pour it out because it's faster. So if you pour it out, are you going to be able to get it all out? No. There's still going to be some residual decantate in there. And the way we get the residual decantate out is by washing it out. So we'll use 10 drops of water and wash our precipitate, and then centrifuge, and then decant the wash into our decantate. And so the first wash we're going to save. I usually do 3 washes, 2 or 3 washes. First wash, save with the decantate. Second wash, throw away, discard, because we want to make sure the silver chloride is clean. Any contaminants on there will screw up our results here. And so I usually wash. It depends. If I'm losing precipitate, I wash maybe only once. If I'm not losing precipitate, I just wash it like twice, 2 more times, let's say. So first wash gets combined with the decantate. Second and third wash gets discarded. It gets discarded because you don't want to dilute or overly dilute your decantate. It's not worth it. Does that make sense? Because the concentration of the ions is too small to worry about. Okay, now we should have nice and clean silver chloride precipitate, and the decantate should be in a separate test tube over here, ready to be analyzed. We're going to continue with the silver chloride. The first thing we're going to do is we're going to add ammonia. The purpose of the ammonia is to dissolve the precipitate. We need to dissolve the precipitate and form this diamine silver ion, silver 1 ion. So how much ammonia should you add? Well, it says to check it with litmus. Do we have to check it with litmus? No. You know how much ammonia I'm going to add? This is 6 molar ammonia. That I need to know, because we also have concentrated ammonia. And so do we add the concentrated or the dilute? We're going to add the dilute. How much? Until it all dissolves, and then stop. Don't add any more. And so just add enough to dissolve it. If you add enough to dissolve it, do you have to test? No, you don't have to test it with litmus, because the whole purpose of testing the litmus is to make sure you added enough. But if you see that it dissolves with your eyes, then you don't have to test with litmus. Does that make sense? So we're not going to test with litmus here. And how much do we add? We add enough to dissolve all of it. Once we dissolve all of it, then we're going to add nitric acid. The nitric acid is going to react with the ammonia and destroy our complex. When we destroy the complex, it's going to reprecipitate out silver chloride. So how much nitric acid do you add? You add enough to maximize the precipitate. So just keep adding until you get as much precipitate as possible. Actually, you only need a little bit here, because this is the final step. If we needed to use that precipitate for something else, then we'd do that. And so do I need to test with litmus to make sure it's acidic? No, I just keep adding nitric acid until I see a precipitate. And that's it. And if you see a precipitate, that means you've added enough nitric acid. So if we go through this step, we get a white precipitate with HCl, the precipitate dissolves with ammonia, the precipitate reprecipitates with nitric acid. Then this is a positive test for silver ions. So we tested positive, that means there's silver ions present. Everybody should test positive for silver ions with your known solution. With the unknown, you might not have any of this, but the known, you should. Then we're done. Now we could throw this away. Never throw anything away, because a lot of people will throw the decantate away, not realizing that they need it for the part 3 here. In step 3, we're going to precipitate out hydroxides, but we have iron, aluminum, and chromium, but also magnesium, nickel, and zinc will precipitate too as hydroxides. And so what we do is something very interesting here. And what we do is a selective precipitation of hydroxides. We're going to precipitate out some hydroxides, just these 3, but leave the others in solution. How do we do that? We do that by controlling how much hydroxide there is. And so it turns out the +3 cations, iron 3, chromium 3, and aluminum 3, need very small concentrations of hydroxide to precipitate because they're so insoluble. But the +2 cations, magnesium, nickel, and zinc, need a lot more hydroxide. So the more hydroxide we have present, the more precipitates we'll get, the less hydroxide. So we're trying to minimize the amount of hydroxide. Now we can generate hydroxide using ammonia. Ammonia hydrolyzes water, it's a weak base, it produces hydroxide. So we can do that. But what we're going to do is we're going to add some ammonium to that. The ammonium is going to decrease how much hydroxide we produce. In fact, we're going to make the ammonia-ammonium buffer. If we make the ammonium-ammonium buffer, we can adjust the pH. If we adjust the pH, we adjust the pOH, and adjusting the pOH controls how much hydroxide we have. So what pH do we want for our ammonia-ammonium buffer? Now we need to know the amount, because we need to know the ratio. The base to acid ratio is going to dictate what the pH is going to be. And so here we have to adhere to the guidelines that we have. So if we make it this far, to step 3, then what we're going to do is to the decantate, we're going to add ammonium, 2 drops of ammonium chloride. So our acid component's fixed. And then we're going to add 6 molar ammonia to raise the pH. And so the more ammonia we add, the more hydroxide we're going to get in solution. So it's buffered here. And so we're going to raise it until the solution is basic to litmus. So red litmus turns blue around pH 8 or so, maybe pH 9. And so what we're going to do is we're going to use litmus to tell us when we hit the correct pH, which is a lot easier than a pH meter, because the pH meter we'd have to calibrate it and do all that stuff. And since we're just doing this just only for this, we're going to use the litmus here. But the previous steps where it's calling for litmus, that's not worth it at all. This one, it's critical to use litmus because we want it to about pH 8. Does that make sense? So red litmus to blue, stop. And then we have, if you keep going, you're going to get the hydroxide too high, and you're going to precipitate out the others. You might make it this far, you might not. And so I'm going to stop here, and then what you're going to do is you're going to go to the stockroom. They're going to give you 2 test tubes. One test tube is the known, which contains everything. You only need 10 drops for this. They're going to give you a lot more for the other tests. And then the other test tube's going to be your unknown. So what you want to do is you don't want to risk your unknown right now. So just go through the whole procedure with your known, and then when it comes time for the unknown, you'll just work on that alone. For the known, you can work with a partner. For your unknown, you have to do individual. All right. Are there any questions? No? Okay, so this is what we're doing today. Our goal is to get a positive test for silver, and then maybe separate out the iron, chromium, and nickel. Not nickel, aluminum.